Hello, everybody, and welcome to one of our extra sections for this year, which is 3.4. So if you already did the graph lab, which was section 3.1, where you basically use Desmos to graph a bunch of equations and see what they look like and how equations relate to a graph, then this section will be a little bit easier for you. If you have not done that, this section will be probably a little bit more difficult. You might have to pause here or there to go back and re-listen to some stuff or draw a little bit more slowly. I will try and go through a little more slowly than I would normally go through this section simply because some of you might not have done 3.1. But again, if it is too fast, it is a video, so you can pause and rewind or scroll back if you need to. So what we're talking about in this section is different types of functions. So you guys have dealt with linear functions since grade 7, and quadratics you've dealt with quite a bit. You spent half of grade 11 doing quadratics. So we're going to be looking at specifically 3 new types of functions, but they do keep going. We're going to be looking at cubic, quartic, and quintic functions. So just a reminder, if you have a linear function, we say this has a degree of 1. And this looks like a straight line. And an example of a linear function would be something like y equals 3x plus 2, or y equals negative 4x plus 1, something like that. We say this has a degree of 1 because the highest power of x that we have is x to the power of 1. So if we have a positive leading coefficient, so similar to the 3x squared plus 2, these look like a straight line that increases as you read the graph left to right, or it goes up. So something like this. That would have a positive leading coefficient. If you have a negative leading coefficient, similar to the negative 4x plus 1, this would go down as you read left to right, or decrease. And something like that would be a negative leading coefficient. Now remember, these could be positioned anywhere on your graph. So I could have one that goes here, I could have one that goes here, I could have one that goes like this, I could have one that goes like that. They can go anywhere. I have just drawn one possible example. There are an infinite number of positive leading coefficient linear equation lines. So these are just examples so that you know what they look like. Okay. A degree of 2 was a quadratic. So you spent a lot of time in grade 11 looking at quadratics. And when you graph this, this is a parabola. And an example would be y equals 3x squared minus 1, or something like y equals negative 2x plus 3 squared plus 4. So a positive leading coefficient would be similar to the 3x squared plus or minus 1 that I gave you. This means you would open upwards. It's going to be a U shape, and the tails will go in the same direction. So they either have to both go up or both go down. So something like that would be like this. Another example, they do not have to be below the x-axis. You might have something that looks like this. So your U shape does not have to cross the axis. You could have a U shape that is opening up and is completely above the axis. Similarly, you could have a U shape that opens down and is completely below the axis, or you could have a U shape that opens down and crosses the x-axis on its way down. So again, these are just possibilities. The upside down U would be a quadratic with a negative leading coefficient, similar to the second example I drew there, negative 2, and then the brackets, that one. So opening downwards, negative leading coefficient, opening upwards, positive leading coefficient. So our first new one is a cubic. Okay. And basically the next three all look like squiggles. Okay, so this one is a squiggle. And similar to a linear, you're going to have it increase as you read left to right. So what's going to happen is it's going to be like a linear, but with bumps. So if I have a positive leading coefficient, it should go up as I read to the right. If I have a negative leading coefficient, it's going to go down as I read from left to right. The tails will go in opposite directions. Okay, so an example of a cubic would be something like y equals x cubed plus 2x minus 3. Another example might be negative x cubed plus 4. So you might have squared terms, constant terms at the end, but in order for it to be a cubic, there must be an x cubed term, and that has to be the highest degree. So this is a polynomial with degree 3 because you have an x cubed, and that is your highest degree of x. There's nothing bigger than x cubed. Okay. So a cubic might look something like this if you have a positive leading coefficient, and something like this if you have a negative leading coefficient. Now, these are very strong examples of cubics. There are some where the bumps are much, much more subtle. So something like this is also a cubic. And the reason is it's clearly not a straight line. It is not a linear function. And you can see that it sort of curves as you read it left to right, and the tails go in opposite directions. Similarly, you might have it where there are bumps, but it doesn't cross the axis this many times. So you'll see that the one I drew, both of these blue ones cross 3 times. You can have a cubic that doesn't cross that many times. So I could have one that looks like this. Okay. This one, if my x-axis were to continue, this one would only cross once. So it has to cross at least once because the tails are going in opposite directions. Okay. The next one is with a degree of 4. So this means that our highest power of x will be 4. This one is called a quartic, and it either looks like an M or a W. Okay. There are, again, similar to how we just saw that very slight example of a cubic, there are quartics where it's very slight movements, but the very strong examples will look like a W or an M. Okay. So an example of a quartic would be something like y equals x to the power of 4 plus 3x cubed minus 2x squared plus x plus 1. Or something like y equals negative x to the 4 minus 5x. That's also a quartic. Okay. So a quartic with a positive leading coefficient is going to open upwards, similar to how a quadratic with a positive leading coefficient opens upwards. The tails need to go in the same direction. So when I open upwards, I'm going to look like a W if I have a very strong example of a quartic. It might be a very faint W. That can happen as well. So a very strong W would look something like this. Okay. But a more slight example might look something like this. Okay. So you can see that the quartic could cross up to 4 times, but it might cross no times if it's like the red one. Okay. If I have a negative leading coefficient, it's going to be upside down like an M. Okay. The humps do not need to reach the same altitude, so to speak. Like they don't have to go up as high as each other. One might be lower than the other. And you can see here that this one only touches the x-axis once. So that's possible as well. Again, you might have one where they're really lopsided and kind of funky looking. So something like this, that is also a quartic. Again, it's clearly not a quadratic. It's not a U. You've got that little extra bump in there. Okay. And the last one that we're going to be looking at is going to be your quintic. And this means that your highest power of x is 5. So something like y equals x to the 5 plus 2x minus 3, or y equals negative x to the 5 minus x cubed plus 4. Those would both be quintics. Again, you could have other powers of x in there. This one, the first one, you've got just an x, and then the next one, you've got an x cubed. There could also be an x squared, an x to the power of 4. But the key here is that the biggest power is x to the power of 5. So for a quintic, you're going to have tails that go in the opposite direction. And again, if it's a positive leading coefficient, it's going to look like it goes up left to right. A negative leading coefficient goes down left to right. Okay, so that would be a positive quintic. A negative quintic might look something like this. Again, like all the other ones we've seen, you could have much more slight examples. And you'll notice that you have 1, 2, 3, 4, up to 5 x-intercepts, but as little as 1. So on all the odd degree functions, you have to have at least 1 x-intercept. The tails will go in the opposite direction. Okay. For your even degrees, you could have no x-intercepts. You either open up or you open down, and the tails go in the same direction as each other. Okay. You'll also hopefully have noticed that the most number of x-intercepts we can have for any degree is the degree. So the most number of x-intercepts you can have for a quintic with a degree of 5 is 5. The most you can have for a cubic with a degree of 3 is 3. So these are going to help us graph polynomials from equations today. There's going to be two main ways we're going to look at this. One is simply to make a table of values, and the other one is to use a factored form to find our x-intercepts and graph that way. So knowing what these should look like when you're done and what direction they should be going is going to help you and make it less work. You don't know these generalizations, you're going to need a lot more points in order to have an accurate graph. If you know generally what they should look like, it's going to be a lot easier to connect your points and know where your curve needs to go. So we're going to do 4 examples today, 2 where we need a table of values, and 2 where we're going to use the x-intercepts. So these first 2, they are not factored. We can choose to factor if possible, but we only want to do that if it's very obvious and easy. So this first one, for example, I'm going to move it down here. This first one, it's very obvious to see that we can factor out an x squared. So if I do that, it's going to save me a little bit of time. So if I factor out an x squared, I'm going to also take out a negative. I'm left with x plus 3 in my brackets. And we know from way back in grade 11, when we did factoring quadratics, What this means is that to find an x-intercept, your x-intercept happens when y is 0. Which means that one of your factors would need to equal 0. Here, one of my factors is x squared, and the other factor is x plus 3. So for us, that means either x squared equals 0, which would mean x is 0, or you have x plus 3 equals 0, which means x equals negative. So these are my x-intercepts. Now, the other thing that you'll notice is that this is a cubic. So technically, we should have 3 factors. When we have a quadratic, we have 2 factors. So if we have multiple x-intercepts, we should have multiple factors. So here, x squared technically means we have 2 x-intercepts as x equals 0. We call this a multiplicity. Okay? So this one here has what we call a multiplicity. Oops, missing half the letters. Of 1, because there was only one factor that was an x plus 3. This one here has a multiplicity of 2. Now that's going to help us graph. When we have a multiplicity of 1, it means we're just going to go straight through that x-intercept like we normally do when we graph. If we have a multiplicity of 2, that means we're going to touch the x-intercept and then turn back around. So sort of like if we had a vertex on the x-axis when we draw a parabola, you touch the x-axis and you turn back around. Similar with our multiplicity of 2. Basically, you're going to touch the axis and turn around. This will be true for any even multiplicity. So if I have a multiplicity of 4, I'll touch and turn around. If I have a multiplicity of 3, I'll go through it like my multiplicity of 1. Okay. So I also can use these equations to find y-intercepts, which can help us graph as well. So I know that my y-intercept happens when x is equal to 0. So if I plug x equals 0 into this equation, that means my y-intercept would be 0. Because if I plug x is 0 in here, I get 0. So I actually have quite a bit of information. I know that I have an x-intercept at 0 and at negative 3, and my y-intercept is 0 as well, which makes sense once I've put my x-intercept there. Okay. Now, so far, this doesn't make sense with what I need to graph. I have to graph a cubic with a negative leading coefficient. As soon as it has a negative leading coefficient and it's a cubic, this tells me it needs to look like this. Right? So I only have 2 points. This is not enough information. But I do know that my tail needs to go up off to the left and down off to the right. And I know that I don't cross the x-axis anywhere else. I know that from my multiplicity, I need to touch and turn around at 0, and I need to go through negative 3. So what this means is if I touch and turn around at 0, I can either be touching and turning around like this, or I could be touching and turning around like this. And the question is, which makes sense? Well, if I look at what my graph's supposed to look like, my tail is supposed to go down as I go to the left, or sorry, as I go to the right. So if I look at these two, my red version, my tail would go down this way, but my blue version, my tail goes up as I go to the right, which makes no sense. So this tells me a lot of information about how I should be graphing this. I know my tail needs to go down as I go to the left, and I need to touch and turn around on that axis. I also know that at some point I have to be able to go through my other x-intercept. I could either go through this way or I can go through this way. Those are my 2 options, right? Again, if I look at what I know my graph should look like, my tail should go up off to the left. So the blue version makes sense here. So the only thing I don't know is I don't know how far down does the hump in the middle go. Does it go way down like this? Does it go really shallow like this? We don't know. So we need a couple more points. So we're going to make ourselves just the tiniest little table of values here. And what I'm going to do is I'm going to plug in x is -1 and -2. So I'm going to put my tiny table of values just over here. So I need x's -1 and -2. And if I plug those into y, when x is -1, what do I get? I get -1 cubed, which is -1 times -1 is 1 minus 3. I get -2. Right, so that tells me some information there. And if I plug -2 in, I get 8 minus 12, I get -4. Okay. And there we go, we have a graph. Now, the other way you could do this was just to make a giant table of values. You could just make a massive table of values and start plugging in numbers, putting points on your grid, and connecting. That's what we're going to need to do for the next one because we can't factor this guy easily. Okay. So for the next one, I don't have enough information to be able to factor this and be able to um, graph this really easily like we just did the blue one. Again, the blue one, we spent a lot more time than most of you would probably actually take to do all of what we just did. We went through it very slowly. Some of you might need to go through it that slowly, but many of you will not. So this next one, the first thing, I can't factor out anything nicely, but I do know it's got an x to the power of 4 with a positive leading coefficient. It should look like a w. And my y-intercept is when x is 0. If I plug 0 in for all my x's, I get that my y-intercept is 3. So I know that much. Okay. Now, other than that, I know nothing. I need to make myself a table of values. Okay. So I'm going to pick maybe x is -1 and 2, and then maybe x is 1 and 2, and start with that. If you start getting really massive numbers, don't keep going that direction. So if I plug in -2 and I get something completely ridiculously large, I'm not going to go and pick -3 because that's telling me my tail is going up off that direction, and I'm just going to keep wasting my time going forever. So I'm going to start with -2, -1. I don't need to do 0. I can add it to my table, but we already found 0. It's 3, and 1 and 2. So I'm going to start with that. All we're doing is we're plugging those numbers in for x. So -2 to the power of 4 minus 6 times -2 cubed plus 8 times -2 squared plus 3. That gives me 99. I am not putting that on my graph. And I'm not going to try -3. I don't need to keep going. I'm good. Then I'm going to try -1. So I'm going to plug this into my calculator. I get 18. Okay, so that's huge. That means this tail, this is going up here like really high up. I can't even put that on my 18 is too big. It's going way, it's shooting up really, really, really straight up. Okay. Now I'm going to try +1. If I plug in +1, I get 6. So that's much nicer. I can put that on my graph. So that means that I must be going up towards my 6. This is good. I'm supposed to look like a W, so this is good information. And I'm going to do 2. So again, we're just plugging 2 in for our x. So we're going to have 2 to the power of 4 minus 6 times 2 cubed plus 8 times 2 squared plus 3. That gives me 3. Okay. Now we can't assume that this is just going to turn around here. It might keep going down to the right. So I'm going to pick another x value and see what happens. If it starts going back up, then we're done. If it keeps going down, we're going to need another value. This gives me -6. So this is way down here. 1, 2, 3, 4, 5, 6, way down here. So I'm going to need, again, one more value here. If I plug in 4, plug this into my calculator here, I get 3. So I go back up. This is good. So once I go back up, I know that it's got to keep going back up forever because it's supposed to W, so it can't go back down. So some of you might go, well, then why did we even start with -2? We didn't have to. We could have started with -1 and 1 and then see what happens. The -2 does reinforce, though, that the tail's going to keep going that direction, since I hadn't gone over to the right yet. So these are a little slow. Table of values, you're plugging in numbers and just trying. Okay. The other type is if you are given an already factored question. So the first thing you need to look at is how many factors do you have? Like how many x's do you have? And that's going to tell you what type of graph it is. And you need to look at your leading coefficient. Is it positive or negative? So that you know if this thing is going up, down, if it opens up, opens down. And then you need to figure out where your x-intercepts are and what your multiplicities are for those x-intercepts. And that will help you graph these. So the first one, I'll go down here. We've got y equals x times x minus 2 times x minus 3. So if I take a look here, I've got an x-intercept at 0, 2, and 3. 0, 2, and 3. I also know there are 3 factors total, so this is a cubic. There's a positive leading coefficient. So I know that it needs to look like this. Okay. So if this is what it needs to look like, that means my leftmost x-intercept would have to have a tail going down this way. Okay. My rightmost intercept would have to have a tail going up this way. And we would be traveling between those somehow. So the only thing is that we don't really have any information of, again, is this a little hump like this? Is this a big hump up like this? And where does it go in between? So between those two intercepts that are really close together, if you really want, you could plug in 2.5, but I don't expect you to do that. You can just connect these if you'd like. Well, maybe not like that. Let's try that again. Okay. But if you really want to be very specific, you could plug in 2.5 and see what you get. What we really need to know is we need to know what's happening here in the middle at x is 1. Okay. So I'm going to try x is 1 in here and see what my y value is. So I just had that one additional. So I'd have y equals 1 times 1 minus 2 times 1 minus 3, which gives me 1 times -1 times -2, which gives me 2. And then I have enough, I can connect by, and I'm done. The next one, okay, same thing. We've got x-intercept at -1, 1, and 2. And you will notice that we have one of these special x-intercepts here. This guy here is squared, which means it has a multiplicity of 2. That means at that x-intercept, we are going to need to touch and turn around. The other ones we can go straight through like normal. If we had a multiplicity of 3, we would also go straight through. If we have a multiplicity of 4, we would also touch and turn around. With the multiplicity of 3, sometimes you will see like a slight squiggle as you go straight through. But anyways, so we have 4 x-intercepts technically. 3 different numbers, but on the x plus 1 squared, that's technically 2 x-intercepts in one there. So we have four factors: x plus 1, x plus 1, x minus 1, and x minus 2. So this is a quartic. It has a positive leading coefficient. So it should look like a W. So I'm going to put these x-intercepts on my graph. I've got x-intercept at -1, I've got one at 1, and I've got one at 2. Okay. I know that I need to touch and turn around for the first one. Okay. So again, I'm either touching and turning around from here, or I'm touching and turning around from here. Since this is a positive leading coefficient, it should look like a W, which means when I leave the leftmost x-intercept, I should be going up. And when I leave the rightmost x-intercept, I should be going up. I know that I need to touch and turn around for this one, and I know that I'm going to go through the other two. So again, the only thing we need to know is in the middle here, how high up do we go? So that would be when x is 0. I want to know information about that. So we're going to try, if x is 0, what do we get? So we'd have y equals 0 plus 1 squared, 0 minus 1, 0 minus 2, which gives me 1 times -1 times -2, which gives me 2. And we can connect. So sometimes you might need just 1 or 2 extra points to help you there. But overall, once you have your x-intercepts and you know like where your tails should go, you can draw most of your graph. And that's it for graphing polynomial functions. There's a practice sheet you can try if you want that just has a couple other graphs on it, or there's the board questions that you can try today. You can also find questions from your textbook if you like, and there's graph paper posted online.